mathematics, I think everybody is expert. I don't think I need to go into the motivation and all these things. But let me quickly go through just to set up the notations what I am going to use in this talk. So this is some motivation for unitary matrix model. It appears both in physics and mathematics. It has, especially for high energy phase theory, this unitary matrix model is important. For example, different supersymmetric gas theory will boil down to this unitary matrix model. For example, Chomsky theory, which I am going to talk about at the end of this the last part of this talk. And also in mathematics, it has a great importance. The non-trivial zeros, there is a strong connection or similarity between non-trivial zeros of Riemann zeta function and the distribution of eigenvalues of unitary matrices. If time permits, I will say a few words about this last point at the end of the talk. So this is just a couple of, I will just show a couple of slides on unitary matrix model just to set up the notation. So this is the unitary matrix model, sum over all the configurations weighted by this factor. Hard measure, du is hard measure, su is action. So since both du and su are invariant under unitary transformation, therefore you can go to a diagonal basis where you can write u as e to the power I theta I. There are n number of eigenvalues theta 1 to theta n, and in this diagonal basis hard measure takes this form. And also s of u becomes a function of n variables theta 1 to theta n. So this is very well known. As I was telling, different supersymmetric gas theories, some compact manifold boils down to unitary matrix model. This is at zero. This is the form of the unitary action at zero coupling. It's a trace u dagger n, sum over n. An's are function of temperature. Also, there is another form which I will be mostly talking about in this talk. This is called some single plateau model, generic single plateau model. Beta n's are some parameters. So it's trace u n plus trace u dagger n.
What is beta in the plus?
Beta n?
What is beta in the plus?
Oh, beta is inverse temperature. Sorry.
So what is on S3?
That is S3.
No, it is on S3.
Oh, S3, there's a temperature also.
Oh.
Okay, so the S3 plus S1.
Yes, so actually I was going to ask that. So you're in 3 plus 1D, is it?
This is, you can think of this as some unitary matrix model. But if you come from
in terms of the gauge theory,
it's 3 plus 1. So anyway, we are mainly.
I mean, this is just you're just writing down the action for the holonomy, right?
Yes.
That's
So
what
basically,
you integrate out
all the massless modes only the geo mode is massive. Yeah, that is basically the other one. Yeah,
okay.
Exactly. This is at geo coupling, but you can write if you turn on coupling, you will have the other terms order by order in loop extraction. So anyway, this is something called one plateau model, and these two models are equivalent up to the if you identify the beta n equals to beta n equals to a times the excitation value of trace u n. So anyway, in this talk I will mainly consider this action. So before I go into detail, let me tell you what I am going to discuss or our results in one page. Briefly, let me first tell you what the results I am going to discuss in this talk. So this solution of this unitary matrix model basically tells you the different distributions of eigenvalues. Okay. So depending on your values of parameters, you have to turn on some values of parameters, you get a particular distribution of eigenvalues which basically minimizes the partition from minimizes the action or minimizes the free energy. So once you change your values of these parameters, the minimum energy configuration jumps from one distribution to another distribution that corresponds to phase transition. And this is well known that unitary eigenvalues of unitary matrices behave like position of free fermions. At the same time, the unitary matrix model, what I will also discuss in detail, but the partition function of a unitary matrix model you can also write as a sum over representations of unitary group. And in the large n limit, what happens that a particular representation dominates the partition function. So a representation you can cast in terms of Young tableaus. That means you have some number of boxes in a particular rows. So this UI basically tells you a particular distribution of boxes in a Young tableau. So in the large n limit, a particular representation dominates. On the eigenvalue side, in the large n limit, a particular distribution of eigenvalues dominates. So what happens that one can find a relation between this Young tableau distribution and eigenvalue distribution in the large n limit. So this identification actually defines a Fermi surface in a two-dimensional space spanned by h and theta. Okay, and so so therefore different shapes or different topologies of these two-dimensional droplets in this space spanned by h and theta characterize different phases of the theory.
What was H again? Some coefficient in the...
HI is number of boxes in ith row of a Young tableau, of the most dominant Young tableau. Okay, so for SUN group, I have maximum n number of rows. So H1, H2, Hn are number of boxes in a particular row of a Young tableau.
I thought you just get, don't you get a quantum mechanics for the theta i's, which are free fermions?
Well, it's a zero-dimensional matrix model. It's not matrix quantum mechanics.
Oh, it's not even quantum mechanics. Ah, okay. But then,
It's a Coulomb gas. It's a Coulomb gas.
but then what's the? And you can think of, okay, it's a Coulomb gas, and then what is the free fermion interpretation?
Yes, I mean, okay.
A Coulomb gas.
At this point, it's what you can say. Different phases you can characterize in terms of some droplets in H3. Then the interpretation of this phase space in terms of some quantum mechanics, it's I think yeah.
So in the second line, when you say unitary matrices behave like positions of free fermions, where does that come? Is it just because there's repulsion?
It's because of the repulsion.
Okay.
I mean, you're saying that there's some potential which is log or whatever it is.
Yes, I will show you. Yeah, there is some potential which basically tells you some repulsion between the eigenvalues.
And this H theta, I haven't quite understood. You're going to give more details later?
Yeah, I will give more detail. Okay, so this is the matrix model we are going to consider. Okay, so this I can write in terms of d theta i's and then some s effective. So this part comes from President plus President dagger, and this part comes from the Van Neumann determinant. Okay, so this, as we were telling, you can think of it's a system of n particles. Okay, there is a interaction between them which goes as log of sin theta minus theta j, and there is a common potential for all the particles which is given by this.
Why is it two-dimensional? I'm still not clear.
Why is it two-dimensional?
Why is it two-dimensional?
Oh, I know it's a two-body repulsion.
The log is the Green's function.
Oh, that's what you mean, that you would get a log for in two dimensions. Is that
For Green's function, yes. It's basically interaction between two-body interaction.
two-body, okay.
Two-body interaction. Okay. So now let's talk about very briefly the eigenvalue distribution. So because of this strong repulsion term, two particles or two eigenvalues, better to say, for two eigenvalues cannot come close to each other. Okay, so if you neglect the Coulomb repulsion, this repulsion log of this theta minus theta j repulsion, then given a potential, what happens that all the eigenvalues come and sit at the minimum of this potential, but since there is a repulsion, they will repel each other and they will spread about theta equals to 0 point. Okay. So that basically tells you the distribution of eigenvalues. So to denote the distribution, we introduce these eigenvalue distribution function rho
You know,
theta.
how did they become fermions? I mean, I can
Oh
understand
no,
that.
yes. This it's not whether it's fermion or not. It's not yet. It's just some eigenvalues. Okay, because of the repulsion. Okay, they spread about theta equals to 0 point. All the eigenvalues cannot come at theta equals to 0. It's just because of the repulsion they spread about theta equals to 0 point. I think this is kind of motivated by the fact that this Vandermonde determinant goes and sits in front of the function of this. That is in quantum mechanics.
That's what the unitary quantum
mechanics.
quantum mechanics.
Yes, exactly. So yeah, at this point it's just eigenvalues. There is a repulsion between them. Okay, and they spread about theta equals to 0 point. And because of this repulsion, you may think of, I think these are like behave like coordinates of fermions.
They just say they don't want to sit on top of each other.
They just don't want to sit on top of each other.
But that's a matter of dynamics. I mean, it's not like a delta function. It's not like this equivalence between hard sphere bosons and fermions. There it's like a really like a delta function repulsion. Here, this is long range.
This is long range repulsion.
So it's not clear that in any case. I mean, it's also these guys. Even if you take into account the Coulomb repulsion by saying that these are effectively some fermionic objects, they still have the other term. They still have the attraction. So it's
because of the attraction, you will see there is kind of the density will be higher at theta equals to 0 as you go towards
I
theta
see.
equals
So
to
by free fermion you mean these are non-interacting fermions but
No.
in an external potential.
there is an external potential.
And
Same
somehow the
external
Coulomb
potential.
repulsion you were sort of thinking of as a delta function or something.
Yes.
Okay.
Okay. So this is in the large n limit. This is we consider these continuous variables. X runs from 0 to 1, where I runs from 1 to n, but in the large n limit x runs from 0 to 1, and this is the definition of eigenvalue densities. And you can solve this matrix model and find eigenvalue densities for different phases of the theory. I will not go into the discussion of these eigenvalue densities, but for a particular model, okay, I will just show you pictorially what is the different eigenvalue densities or different phases of this theory. So we consider this particular model beta 1 and beta 2 not equals to 0, all other betas equals to 0, exactly what you showed me today morning. Okay, so this is, the action is given by this. V theta in this case is just cos theta plus 2 beta 1 cos theta plus.
By the way, this paper is exactly at the same time as my paper.
Oh, I see. I am sorry. I am extremely sorry. I missed that. Sorry.
That's okay. It's a long time back, 1990. You were not probably even born.
Sorry, gosh.
It's a
That's
1.7 old paper, yeah. Okay, so I will just tell you very briefly what would be the different eigenvalue distributions. So when you do not have any potential because of the repulsion term, all the eigenvalues are sitting uniformly on the unit circle. So therefore eigenvalue density is 1 over 2 pi. So when you have some potential, there is some depth. If you turn on some beta 1 and beta 2, there is some depth, and the eigenvalues start spreading about theta equals to 0, but the depth is not that much. So basically, the eigenvalues fill this gap, but they are distributed from minus pi to plus pi, and this is the one gap. So this is no gap distribution, no gap phase for this model.
Depending on beta 2, the potential can develop a second minimum at pi is at pi by 2 or pi by 2.
Yeah, that is I will come to that. Will corresponds to some 2 gap or multi gap solutions. So this then again you increase the values of beta 1 and beta 2, the depth becomes more, and then you start spreading the eigenvalues about theta equals to 0. At some point they exhaust, and then you have a solution. All the eigenvalues are distributed between minus theta 1 and plus theta 1. So it tells you one gap solution of this model. So eigenvalues are distributed between minus theta 1 and plus theta 1, and then there is no eigenvalue distribution gaps means if you just think of distribution of eigenvalues, so they are distributed between minus theta 1 to plus theta 1, so there is one gap. Okay, so if you just on a circle, so that all the eigenvalues are distributed between minus theta 1 and plus theta 1, and then there is no gap here. Then there is no eigenvalue distribution here, so it's a one gap solution.
What was it last time?
Last line, so all the eigenvalues are distributed between minus pi and plus pi, there is no gap. So now if you change your beta 1 and beta 2, the potential takes this kind of form. So now you start filling the eigenvalues, since the minimum energy configuration corresponds to you fill up to this point and fill up to this point. So you can see the eigenvalues are distributed between theta 1 and theta 2, minus theta 1 and minus theta 2, then it corresponds to two gaps.
Actually, it's not minimum energy. If you do minimum energy, you will not get the right result. It's minimum
Minimum
free energy.
free energy, yes, yeah. Minimum free energy.
He's minimizing that
Total action, total S, including the log term.
There is no, okay, so the point is there is no V of theta. It's a two-body, there's a two-body potential and there's a one-body potential.
Yes.
You know, so this V of theta, his notation for V of theta was the one-body potential. Now what you have to do is to that you have something like a rho log kind of stuff. So you can make a Hartree estimate in which you replace one of the rows by its expectation value, and then it becomes a one-body potential again. So now you plot that effective one-body potential, and that will show you the right kind of arcs.
Yeah, but basically that S effective you have written, you have to minimize that S effective with respect to rho theta. That gives you some kind of quantification.
Except that there is no one-body representation of that thing at
Yes,
all.
it's
a sum of our. No, but you can actually do this, accurately, in the sense that in a Arden theory, you can approximate that two-body potential by one-body extra one-body potential.
Exactly.
Add that. Anyways, it's probably not.
So that extra one-body potential depends on rho.
Extra one-body potential depends on.
That's right. It depends on rho. So it's self-consistently done only. So you can't quite say that okay, I have computed the free energy and therefore it is this.
Yeah.
In retrospect, you can say okay, this is where it must have been.
You're saying if you have trace U, one of the trace U's can be taken as expectation.
That's right. Yeah.
Okay, and another possibility of two-gap solution is like this. Eigenvalues are distributed about the minimum free energy configuration. So as you are telling, there must be some minima at theta equals to pi. So this one and this one, they correspond to two-gap solution because we have two gaps, this one and since this point and this point are identified, you have basically two gaps, this one and this one, and here you have this gap and this gap. So this is about eigenvalue distributions for this model, which is very well known. Now let me go to
Sorry, if you can just go back. I mean, at least that statement that rho of theta is of this form.
Yeah.
In your Hartree-Fock solution, that's a.
The way you do it is to you solve this rho of theta first. Then you sort of get a physical understanding by saying that can I have a Landau-Ginzburg kind of description of this? But this is what comes by solving that sort of resolvent equation as the
Shannon equation.
You're only telling us about the ground state. I mean, the lowest free energy. There are of course many other saddle points.
Yeah.
So is that right?
Even in Hartree-Fock.
Even in Hartree.
Oh.
So for instance, suppose you have two minima, you could put all eigenvalues around the other minimum. If they fit. That would be a nice solution.
But
You can also have solutions around maximum.
But that is not the lowest free energy solution.
I agree. No, but I'm just saying, suppose you want to find all solutions to the gap equations. That would be nice.
And another thing you should notice that the eigenvalue distribution is symmetric over theta equals to 0. It's just because the partition function we are considering is inverted under u goes to u diagram. Okay, so this is about the side. So now the goal of my talk is to provide a phase space distribution for different phases, what I have discussed. Okay, first of all, although I have discussed these different phases for beta 1, beta 2 model, but if I consider a generic vacuum model, you can have multi-gap solutions. Okay, 1 card, 2 card, 3 card, and so on. So, the goal of my talk is to provide a phase space description, that means a droplet picture corresponding to these different phases, whatever I have discussed so far. Okay, and to understand how topologies of different droplets in a two-dimensional phase space captures information about different phases of the theory and the transition between them, and what is the momentum, so and so on. When I am talking about telling phase space, then some momentum is associated with that. What is that momentum? So this is what I am going to discuss in next half an hour. Okay. So now come to the partition function side. This is the partition function we are considering. You can expand. You can expand the exponential. You can write your partition function in this following. Okay, it's an infinite series. But these epsilons. So these are first of all, these epsilon and z are some quantities. They are given in terms of these beta n's. Okay. And epsilon is basically trace u to the power n whole to the power k. So product over n. Okay. This you can write just expanding the exponential. What is the epsilon? Epsilon is product over n equals to 1. So you have I have beta 1, beta 2, beta 3, all these numbers. Okay. Epsilon is just this quantity. So some kn, so you have a sum over k1, k2, k3 and so on, L1, L2, L3 and so on. So beta epsilon is given by this. Okay. So now, yeah, so this k is a infinite dimensional vector, k1, k2, k3, these are the entries, and it's the same as A. Okay. Now, this epsilon ku
is what you're doing larger or finite?
right now is for an A.
So at some point there will be trace identities.
At some point there will be trace identities.
So this trace u to the power n stops at little n stops at capital N or goes on forever?
It goes on to because it depends on the so if for example if I have beta 1 only, then what happens that k2, k3 everything is 0. K2, k3, k4 everything is 0. If I stop at beta 1 trace u n plus trace u dagger n, then it answers that k2, k3, k4 everything is 0.
I was thinking, suppose capital N was 10.
Yeah.
And you take trace u to the power 12.
Trace u to the power
12.
Trace u to the power 12. Okay.
Now that's not independent. That can be rewritten as a polynomial of trace u squared, trace u cube up to trace u to the power 9. Using trace identity. So this expression that you have is not a unique one. It may not matter.
If you have n equals to 10, okay, and then yeah, what I am telling that this sum goes for any n. What you are telling, if you have trace to the power n equals to 10, then when this small n goes as takes the value 12. Yes. So trace u to the power 12 times k 12 to the power k 12. What is the problem with that?
There's no problem. It's just that you can rewrite trace u to the power 12.
Oh, okay. You can
In
rewrite
terms
so
of
lower
things. You may not want to.
yeah, okay. Yeah, that you can do. Okay. But this is a generic expression for it, and it's valid for any.
It's fine. There's no problem.
Yeah. In fact, I will show you that I will basically integrate out these trace u's actually from this expression.
Yeah, because those expressions that you were talking about, Shiraz, because they involve multi-trace, maybe there's a way of characterizing these fellows as, so if this was a generic action with single traces as well as multiple traces, then of course there's a lot of ambiguity in defining the coefficients. Now suppose that you define these only as single traces only, then maybe.
Okay. So this quantity, I'm using some mathematical identity. This sum over representation is a representation over this unitary group. This chi r is a character of the conjugacy class, where this k vector tells you the number of cycles, k1 number of 1 cycles, k2 number of 2 cycles, and so on. And the permutation is of capital K, where capital K is n k n sum over n.
This you have to go slowly. First, gamma k. What is gamma k?
Epsilon k. So let me write here. So epsilon k equals to product over n raised to the power n to the power k. So I have all these k1, k2, k3, all these numbers.
Okay.
Okay. Then I am telling that, well, I am telling means I am using some mathematical identity, which is sum over r. Okay. I given these fixed numbers k1, k2, kn, all these things, and trace r of where r is the representations of.
Wait, yeah. So I just want to understand it because so trace r of u and r runs. So this object has basically n views. Wait, this product over n.
Yes, product is the product over n. Yeah.
With what values of kn? Oh, so some values.
Some k1 fixed, k1, k2, k3, and so on.
I see.
Okay, so k1, k2, k3 is fixed here. Here also.
Okay, so you've got trace u to the power n, u to the power n to some k. To some k. Okay, fine. And what is this chi r k?
Chi r k is, so now, so given this k1, k2, kn, I define capital K is sum over n, kn. Okay?
Yes.
Okay? Then these chi's are characters of this permutation group is capital K
Yes.
in presence of the cycles, k1 number of 1 cycles, k2 number of 2 cycles, and so on.
And this is the trace.
This is trace of u in this particular representation. So for example, SU, if you take SU2, okay, these representations are basically these half, minus half, and then you have half, okay, half, minus half, here minus half, minus half.
So using the fact that a Young tableau labels representations of the symmetric group as well as of SU.
Yes.
Now, what happens if the number of boxes in R exceeds?
Here, yes. Okay. Yes. That is a condition that. So when okay. First of all, if that that doesn't match, then the corresponding chi is 0.
Right. No, but I was just wondering. Suppose we did SU2 and this number of boxes in the Young tableau is very large.
Number of boxes in Young tableau is very large. Fine. Yeah.
Are you allowed to go to in that permutation group?
Okay. For SU2 you can have maximum 2 boxes. I mean 2 rows.
Yeah, that is what I was wondering. Suppose your number of group, you were doing permutation of 20 elements.
Yes.
What is the rule for that? So representations, permutations of 20 elements are represented by Young tableau
of
20 boxes.
20 boxes.
But won't you allow rows?
No, you don't allow rows in this. You don't allow rows. Okay, but you can add boxes.
But how do that's what I'm not understanding. How did you in the permutations of 20 elements? How do you know you were dealing with SU2 rather than SU3?
The permutation of 20 elements.
No, I thought you go up to n-1 number of.
For SU2 you can have maximum. One rows.
That's right. I mean, for SU3 you have a height of 2.
Height of
And so on.
and so on, exactly.
So what's confusing me is this chi R is there R is a character
Yes, that is
of a permutation group.
yes. Suppose let's fix
of K and elements, right?
Suppose-
Of capital K elements.
Yeah. Suppose let's fix K1 equals to 2 and all other K3, K4
No, I want fixed K1 equals
Okay.
2 and everything. I mean, I want more. Suppose capital K was 20.
Capital K is 20. Okay.
So chi r is some representation
Where you have 20 boxes.
where you have of permutations of 20 boxes.
Foundations of 20.
Symmetric group of 20 objects. That doesn't know whether you're dealing with SU2 or SU3 or
That
SU4.
doesn't know whether you are.
So that presumably will have young tableaus with columns of all lengths.
Well, if you consider Young tableau representation of symmetric group,
Yes.
then you have all possible column. Then you have these columns also.
Yes.
These columns also.
So that R there runs over.
Only representations of unitary group. So you have to calculate chi for these particular boxes.
And what about the other ones?
For those, well, it's a sum of representations of unitary groups. So you don't consider this is not a valid representation of SU2.
So you just set those to 0.
Yes.
Yes.
If it turns out that chi r for these 20 boxes is 0, then it's 0. I mean, this representation, sum of representation is representation of unitary groups. So this times, these sum numbers, this is equals to sum over representation of unitary group, sum numbers and trace r of u. Okay, this number is basically representation character of a symmetric group SA. Okay, given these boxes.
But I'm just asking my question again. When I label representations of a permutation group, it runs over young tableau without the
Yeah,
restrictions.
but this is representation of unitary group. This is not representation of permutation group.
No, I didn't understand that.
This is representation of
That
unitary.
was a character as of the representation of what?
Well,
Character of what?
a representation of unitary group. Okay. Suppose let's say you fix k to be k equals to 20.
Right.
Right. So this is a valid representation of unitary group. We have 20 boxes. This is a valid representation of unitary group. This is a valid representation of your permutation group also.
Exactly. So chi r k is a character of a particular element of the permutation. Is this right?
Exactly.
I would have imagined that those r's ran over all representations of the permutation group.
So maybe I misunderstood. What he's saying is this: you have a permutation group, as you say, but then you ask whether that permutation group has a representation in a given representation of a unitary group. See, like for example, if we took the spin-half representation of SU2, then the permutation group of 20 elements may not have a representation.
May not have a representation of
20 elements are so many.
Exactly.
But if you take some symmetric product of 20 spin-halves, then you get a representation.
Representation of symmetry.
So first he says, okay, you fix your symmetry or permutation group.
Yes.
Then you consider those representations of the unitary group which admit a representation of this permutation group. Now you are summing implicitly, if I understand, in that sum over R only over those representations.
Only over SUL representations.
No, but moreover, only over those SUL representations which admit a representation of your fixed permutation
It
group.
admits, I mean, as I am telling that for k equals to 20, I can have this representation, right? For let's say 10 number of boxes, and this is a valid representation of this permutation group of S20.
But if you are dealing with SU2, the spin-half representation may not admit.
May not admit, in that case my chi will be 0.
In that case, chi will be 0. So implicitly you sum over those representations.
Which chi is 0? This I don't understand. So that was an element that was determined by the representation value of the permutation.
That is
Chi there R is a representation of the permutation group and chi is a character of that representation of the permutation, right or not?
chi is the character of the permutation group
Of the representation R of the permutation. Is this right?
So that's why I'm telling you, a representation of unitary group, okay, is also maybe a valid representation of this permutation group.
So at least, let me suggest the following. You are summing over those representations of the
Yes.
unitary group
Yes.
which admit a representation of the permutation group.
Yes.
Now in those representations, you compute chi R and you take trace R of U
Yes.
and you sum over all set.
This formula is something very suspicious.
Yes.
For instance, if I took two spin halves If I took 4 spin-offs and put them down, as if I put 3 spin-offs and I would have thought that would be 2 of them coupling to singlet and then 1 of them just by
3 spin-offs?
If you anti-Semitic,
I'm not maybe I'm just saying it wrong. Okay, this is what you're saying. You're sure this formula is correct?
Yeah, this statement is valid, it's the correct statement.
Okay, fine.
I mean, for example,
So the sum over R that sum will run over different elements depending on what your SUN is.
yes.
And in particular, if n is large enough, then it will run over all representations.
If you take, I will comment on something like that. Yeah.
Okay.
I will comment on that. Yeah, I mean just to, if I take SU2, then my representation are just these and so on. Okay, so you can have any number of boxes here, but of course in this case total number of boxes is 3. So this is a representation of S3. But S3 has other representations. I am not considering these representations. Okay.
What's confusing is that the identity I know is the other way around. I know a formula for chi R of U in terms of these trace of U's and characters of the permutation.
Yeah, that's
the inverse of that.
Yeah.
I'm not familiar with. Okay.
Okay. Okay, so this is U of R, this is epsilon of U. So I have the 2 epsilons. Okay, I plug this formula, so I will get sum over 2 traces R and R prime, but then I use this identity. So basically, if you do the algebra, partition boundary.
So I just one more.
Yeah, sure.
To make sure I understand. The formula I know is take character of R, chi R of U. Okay. Now this R has some number of boxes in the Young tableau. Let's call that N.
Okay.
Then this is equal to sum over all elements of Sn.
Sum over all elements of Sn.
Chi of Sn. Chi of that element. Chi of R.
Chi of R.
No, chi of little r.
Okay.
Chi of little r times trace u to the power n1 trace u squared to the power n2 and so on. U to the power n1 trace u squared to the power n2 and so on, where n1, n2, n3 are the number of cycles of length 1, 2, 3.
Yes.
In the element R.
Yeah.
This formula I know is true.
Yeah, but this is not
This you're saying is equivalent to that.
It's
This is an inverse of that.
This is the inverse of that. Yeah.
Somehow I can't see it in my head, but you must be.
Yeah.
This is a completely unambiguous formula. I mean, there's no
This is-
issues.
Yeah. This is fine, but yeah, this is different than
This is
this
a
one.
different formula. Okay, thank you.
Okay, so now as we were telling, now if I take strict n goes to infinity limit, okay, then all the sum over all the representation of SUN is also representation of my permutation group. Then I can again use that normalization formula for this, and I can write Z as exactly in terms of these betas. What you have, I think, in your trace dagger in model, you get something 1 over n I by 1 minus 1 over n I product by something like that. But since I am not in strictly n goes to infinite limit but finite n limit, so I cannot really do this. If it is what you are telling, if it is just a sum over permutation group, then you could do that. You could use that identity to write it in that way. But it's not a sum over permutation group, it's a sum over unitary group. So where all the representations are not representations of chi, representations of permutation group.
Okay.
Okay, so now in this sum over R you can cast in terms of Young tableaus. K is the total number of boxes. So partition function basically takes this. So Okay, and in the large n limit, one can extremize the partition function with respect to these lambdas. Lambdas are number of boxes. Lambda is a number of boxes in ith row of a representation or ith row of a Young tableau. Okay, and so therefore in the large n limit, you can extremize this.
Wait, so the n result columns, you take product of basic use and write them as characters of irreducible representation.
Yes.
And then in the end, you're doing an integral of the Haar measure.
Yeah, in the end, I'm doing integral over.
And so only the identity will come.
Only the identity. Okay.
This is counting signals, basically. Basically, a counting signals.
Right.
Lambda is and find dominant representations. So the difficulty here is to find the character. If I tell you a particular representation, particular lambda 1, lambda 2, lambda n, and if I tell you k1 number of 1 cycles, k2 number of 2 cycles, and so on, it's difficult to find these characters.
I missed what the lambda vector was.
Lambda is a number of boxes in the ith row of a Young tableau. Okay. So in this paper with Rajesh, we considered a very simple model, beta 1.
Sure. Did you have a final formula at some point for your partition? This was final.
Yeah, sure.
Chi
lambda. Okay. So chi lambda for this particular set of boxes in presence of k1 number of 1 cycles, k2 number of 2 cycles, and so on. Chi lambda for the same set of boxes, L1 number of 1 cycles, L2 number of 2 cycles, and so on. And number of boxes should be equals to nkn, number of boxes should be equals to lnn.
Lambda summed over everything, and what else depends on lambda?
Lambda sum over lambda vector means sum over lambda 1, lambda 2, lambda 3, and so on. But here I put the delta functions.
Yeah, and what are these epsilons again, please, at the z?
Epsilons are just function of some betas.
Okay, and z's?
Z is also some of them. Okay. So if you consider this simple model, beta 1 not equals to 0 and all other beta 2, beta 3, everything is 0, that means your action is just SUN plus SU dagger n. So in that case, what happens that, as I was telling, in that case, all this K2, K3, K4, everything is 0.
Right.
Okay, only K1 non-zero. So that means you have to calculate character in terms of K1 number of 1 cycle. Okay, for a given lambdas. That is very easy to find. This is nothing but the dimension of the representation. Okay, and it's given by this.
Okay, it's identity.
Yeah. So these HIs are just some lambda is some shifted number of boxes in the ith row. Okay. Then you plug this character there, and you go to the large n limit, define these continuous variables, and then you extremize the effective action. So this is the saddle point equation you get for U of h. You can solve this saddle point equation. I am running time actually. So you solve this saddle point equation, and you find what is the dominant representation in the large n limit.
Wait, I didn't understand. Where does this Young tableau density come from?
Oh, I have defined it here. Okay, so okay. So I have HIs, so I am defining h of x as hi by n. Okay, and your density, non-tableau density is minus del x del h. Minus sign is because h is a monotonically decreasing function of x. Number of boxes, okay, number of boxes always, lambda always remains same or decrease, but hi always decreases because there is because of this I factor. So h always decreases. So therefore del x del h is negative. So that's why I put a minus sign. So that this u of x is positive.
So what I don't understand, sorry, this what representation? I thought in the end we were just going to look at this number of singlets.
So in larger limit,
So you couple the products of trace use to get characters of some representation, but only the singlet contributed, right?
this singlet contribute. Now why are you telling all this?
Because
you are measuring, you are integrating with respect to the Haar measure, and you are taking products of, you have exponentials of traces and blah blah, you're bringing them all down, and then you're integrating with respect to the harmonizer. So that's precisely projecting onto the singlet.
Understand that.
So just to understand what you did, you took the exponential, you brought stuff down,
Yes.
then you rewrote all those products of use in terms of characters, right?
Yes.
Then you have to do the integral over U of the characters.
Then I have done the integral over character is.
Why you have two characters? I don't understand why you have two characters.
So you have two epsilons.
Oh, first you take one trace U and then another trace U bar.
Yeah.
I see.
Yeah.
So you do it twice.
Yeah.
Okay, now what?
Okay.
Oh, I see. So then you match in each sum. You match.
Yeah.
this
So
guy,
you basically get sum over R trace R of U, and then also you get sum over R prime trace R of R prime of U data. Then you do the U integration. This gives you delta R prime. So basically sum over one representation is basically left over. Okay, so in our paper, what we found that there is a relation between these eigenvalue distributions and Young tableau distributions, okay, for different phases of the theory, and rho theta, the eigenvalue distribution is basically given by h plus minus h minus by 2, and Young tableau distribution u of h equals to theta over pi. It's kind of inverse relation, but this h plus and h minus are given by this. Okay, so this identification actually allows us to write the eigenvalue distribution and Young tableau distribution in terms of a constant phase-space distribution function omega h of theta. So omega h of theta is 1 inside some region, okay, and 0 outside. So if you integrate over h, so you basically get if your omega is something like this, okay, 1 inside 0 outside, then for a fixed theta, if you integrate it from radially, then this is your h minus, this is your h plus, so you get rho of theta is basically h plus minus h minus by 2 pi, and if you integrate it over theta, you will basically get u of h. So phase, for a particular phase, eigenvalue distribution and Young tableau distribution is captured in terms of these droplets I have drawn in h theta plane.
These droplets are something we invent.
These droplets are something we invented.
Sorry, can you go over this logic again? So go back to the previous slide. Okay, so what are we doing now? U of h is the Young tableau density in the large n limit. Young tableau density. So h, you are making that into sort of a continuous.
Yes, h of x is
Oh, I see. So you're drawing more larger and finer and finer Young tableau.
Okay. In the larger limit is something like this.
It's the edge curve of this.
Yeah. So this u of h basically tells you this curve.
Okay, right. These HIs, if I remember right, these HIs are the boxes in the dual Young tableau, isn't it? If you start with lambda i's and then switch the rows and columns, then don't you get HIs? I mean, I'm saying that how did you get this interpretation? How did you get this interpretation that the profile?
This profile.
Yeah. How do I know that u of h describes that?
Yeah, u of h tells you how h changes with x.
How h changes. So what is the interpretation of h?
H is this. H is number of some shifted number of boxes. So del h del x equals to del lambda del x minus 1.
So what is lambda I?
Lambda is the number of boxes in ith HI is a shifted
H
term.
is the number of boxes up to
Up to some shift, yeah, up to some shift, yeah. H you
up to some I dependent.
up to some X.
So I is your y-axis in the droplet plane.
I is my, yeah, I equals to 1 is this, I equals to n is this, X equals to 0 is this, X equals to 1 is this.
Right. Now you are, so the HI fellows are just the, so I understand that the HI profile, H as a function of y,
H as a function of X, yeah.
X, okay. So that is this curve.
H as a function of X, this is this curve, yeah.
H as a function.
H as a function of X, so it's basically the derivative of, inverse derivative of that quantity.
Okay, so now,
So in principle, if I tell you u of X, okay, you can find H as a function of X.
alright, fine.
In principle.
Okay, got it. So you get some continuous curve, u of x from this, which you are calling u of h.
Which I am calling u of H, yeah.
Okay, so del h, del got it. Yeah, okay, fine.
I mean, it's like rho of theta you define 1 over n delta theta minus theta. In the large n limit, it goes as del x del theta.
Yeah, no, that I got. And now you're saying that u of h satisfies the same resolvent equation as you would have got for the eigenvalue.
No, for eigenvalues, you have cot of theta minus theta prime by 2.
No, so then tell me about the identification of E2
Oh,
with
you
the
solve this equation, okay, and u of h for one no cut solution, if I remember correctly, it's cos inverse h minus 1 by n into beta for one cut no cut solution. Okay, if you take the inverse, it will becomes h equals to 1 plus some factor of 2 pi is missing here and there. Cos of
okay, so right. But how are you identifying this with with rho of theta later on in the next slide? Yeah, what is this? How do you get this?
Oh, this is for a generic phase. For example, if you consider one cut phase, one gap phase of this beta 1 model, okay, one gap phase of beta 1 model, you get u of a 1 plus something, okay, 1 plus 2 beta 1 cos pi u of h, okay, plus something equals to 0. So u of h is given by this.
Yeah. How do we know that u of h is theta by pi, for instance?
Oh, this is where we are identifying. This is where identifying. If you do this identification, then there is a relation between this u of this eigenvalue distribution and Young-Taylor distribution. This is something we are identifying.
It's from the solution.
From the solution. I know the solution in the eigenvalue side, I know the solution in the UH side, okay, then I see this identification.
And in general, if you have general beta i's, presumably you can't solve. So, but you can still make this identification.
Yes, that is what I am going to take.
Okay.
That is what I am going to. So that's what I am telling that this identification was somewhat accidental. Okay, we just found this identification.
Okay.
What I am going to show you that for a generic beta 1 in vacuum model, I get this equation.
That's a
Okay.
So, I just want to make sure I understand. So, suppose I wanted to produce, suppose I knew the eigenvalue distribution and I wanted to produce your tablet. So then what I'm supposed to do is to say theta is u of h. And is there a way of getting, I can't see it from here. Is given, suppose I give you the eigenvalue distribution, will you be able to produce a tableau for me?
No.
Oh.
Either you tell me the generic relation like this.
This relationship you say is always true, right?
Exactly. I will show you.
Given this relationship, is it sufficient to take an eigenvalue distribution and produce a tableau?
Yes. That is what our case.
What is h plus and h minus?
are like the two edges of a droplet.
Two edges of a droplet.
In which you are not drawing horizontals, but the y equal to x line, because you have some funny shift in between your u and the h.
Oh, I mean, the phase space I am drawing in h theta plane.
Yeah, so in here just draw h plus and h minus for me, please. So draw a droplet over the
for example, if you consider no gap solution,
yes,
okay,
yes,
rho theta equals to constant, let's say.
okay,
So for no gap solution, h minus equals to 0. Okay, for no gap solution, h minus equals to 0.
or h minus is equal to minus h plus.
No, h minus equals to 0.
So just plot for me what are the h.
So so this is for rho theta equals to constant,
Yeah.
and this is for your rho theta equals to.
No, but so for rho theta equal to constant, which is like that, let's say. Now you are supposed to draw a vertical line, and it cuts this.
For a fixed theta, it cuts exactly at 1. Okay.
Oh, your theta. Oh, you are doing polar.
This is a polar.
Oh, I see.
Polar.
Okay.
How does this diagram include a tableau? Which tableau is it including?
So given this distribution, okay, I can use this relation. I get what my u of h is. Okay. So given this distribution, I will integrate out over theta. I will get u of h. Okay. So once I know u of h, I know the profile. U of h is del x minus del x del h. So in principle, if I tell you u of h, you can tell me the profile.
Okay.
Okay.
For instance, which tableau dominates for the no gaps? For the uniform function.
Yeah. For no gap solution, I think something like this. Okay. At some point. So this distance, it depends on what is your value of beta 1. Okay. So up to something, you have a completely filled Young tableau, and after that there is no box. So this corresponds to rho of theta equals to 1 plus 2 beta 1 cos theta. Okay, and then you increase beta. Okay, what happens that these gaps decreases. Okay, at some point you come here. This particular point corresponds to your no gap to 1 gap jump. Okay, so that corresponds to some kind of Gauss-Witten-Warrier transition. And then for no gap, 1 gap solution, you have this kind of diagram. So order n number of boxes from here to here.
And the completely flat solution was
Completely flat solution. So u of h. So yeah, we can write to u of h for 1 gap. So no gap. Cos inverse h minus 1 by 2 beta. Okay. So exactly beta 1 equals to 0. Well, probably the solution I have got for beta 1 not equals to 0. We get a trivial solution for beta 1 equals to 0.
Thank you.
Okay. So yeah, so this is what we got in this the one with Rajesh long back, and the second one is with Parikshit. So we also did the same thing for 2 gap solution. But relation between this eigenvalue and Snelling Young-Tableau distribution was an accident. Okay, we do not know if the relation holds for any generic matrix model or not. Okay, this means we do not know if the phase space description of unitary matrix model is universal or not. Okay, so think I have exhausted the time.
Go on.
Okay, fine, thank you. So, so for generic matrix model, as I said, the problem is with the character. We do not know the exact form of character when I have arbitrary number of cycles, k1 number of 1 cycles, k2 number of 2 cycles, and so on. So let's write down what character is. So I introduce this n number of variables x1 to xn. These are some auxiliary variables. I introduce these two polynomials, okay, and then the character is given by this. This is Frobenius formula. So this means this is a polynomial, okay, and this notation means the character is given by the coefficient of x1 to the power h1, x2 to the power h2, xn to the power hn term. This is Frobenius formula. Okay. Okay, so these are some two polynomials. Once I introduce these auxiliary variables,
The character again of what?
character of that chi of R, what I was doing, character of
An element of the permutation.
similar function. Yes.
And h and k again. K is the number of cycles. That's the element, and h is what?
H is the number of boxes, or shifted number of boxes. H is hi, you remember, lambda I plus n minus I.
Why does h never make it?
Huh? Why?
The permutation group depends only on the total number of elements.
Now, permutation group also depends on what kind of arrangements. Character also depends on what kind of arrangement of boxes you are taking.
Yeah. So it depends on the number of elements and which element of the permutation.
Number of element, total number of
Oh,
elements.
and which representation.
Yeah, which representation.
Yes.
Okay. Fine. So, but you see, it's not easy to calculate this character. If I tell you a k1 number of arbitrary number of cycles, it's not easy to calculate this character. So what we did, we promote these auxiliary variables to complex numbers, z1 to zn, and this character we have written using Cauchy formula. Okay. So what I have done, I have just taken everything in the exponential and used this taking logarithm of all these quantities. So this I have written in this way. The character I have written in this way. You do this integral, in principle you will get the character. Okay.
That pj was what? That pj is something.
Pj is the sum polynomial.
Okay.
Fine. So again I go to large n limit. I define these continuous variables zx and this k prime n. Okay. So all these k's are integers, so I take the n square factor out. I define in the large n limit. I define this k n primes. The character is therefore given by sum over these j dice product over I sum over j dice. I have written it like d of z by j of x. The exponential of this quantity, which is like this. So now, in the large n limit, the dominant contribution will come from, you extremize this thing with respect to j dice, okay, with respect to zx, sorry, in the continuum limit, and then this is the starting point equation you get for zx. And you remember the original, okay, the original contour is about z equals to zeta equals to 0. Okay, so I take a circular contour, I take zx to be e to the power I theta x. So I plug that value and I get this equation. So these thetas are still auxiliary variables because j's are auxiliary variables which I introduced to write Frobenius formula. What I do, I take imaginary part of this equation. This is what I take. Okay, and one can show that this is some we have done in our last paper. In the paper, this combination is exactly nothing but beta x. So this equation you can definitely identify. This is nothing but the eigenvalue density equation.
How did the cot come about?
Okay. So in fact, you can integrate over hi's okay, in this partition function.
Derivative of log sign.
Huh?
But where he had log sign? Did he have log sign in the previous?
No, now I think it's going back to reminding us what the eigenvalue resultant equation is. Right?
Yeah, this is the eigenvalue equation. This is the eigenvalue equation.
Oh, I thought
So
you
it's
had
not coming from here.
Oh, yeah.
No.
Okay.
This is the eigenvalue equation.
Sure.
Okay. And in fact, what you can show that is in this partition, you take this time, plug it in the partition function, integrate over HIs. Okay. Whatever you get, that is exactly the partition function written in terms of this theta is.
Wait, I haven't understood any details, but is what you're doing, you've got one problem in terms of H's, another problem in terms of rows, and you've done a variable change to turn one problem into the other. Is that what you're doing?
Say again.
You've written the partition function as some sum over H's or something like that, right? Sum over n terms.
Yes.
You've got another expression for it as a sum as an integral over eigenvalue distribution.
Yes.
And are you doing a change of variables on one problem to turn it into the other one? Is that what you're doing or not?
I have this.
Yes.
I have some chi's.
Yes.
Okay. This chi I have written in terms of dj chi and something.
Yes.
Then I am maximizing this with respect to z.
Yes.
I am getting this equation.
What is theta?
Theta is z is e to the power I theta I have taken because z this when I wrote this using this
I see the contours and so on.
so the z is e to the power I theta.
Yes.
So now I take, so this is the equation I am getting from valuing this is effective. So when I take the imaginary part of this equation, I exactly get back the eigenvalue equation.
So the eigenvalues were the Lagrange multipliers
Of this for this ordinary form. So
For
whatever auxiliary variables I introduced to write down the character, those auxiliary variables are nothing but the eigenvalues of
and
that.
the sum that you had in the original problem, where did that go? You had some sum over something.
This one you are telling?
No, you just yeah. Before you introduce the theta, just before you introduce the theta. Yeah, there's some sum over n. Yeah.
Sum over A.
Oh, that became the sum over n on the other side.
Sum over beta and sin n theta. This is the v prime of theta. Derivative of the potential. Okay. So this is exactly the eigenvalue equation. Because your potential was cos n theta, beta n by n cos n theta. On the right hand side of the eigenvalue equation, you get v prime of theta. So basically beta and sin n theta.
And what was the corresponding equation in the last slide for in terms of the z variables? Okay, that had some structure like that.
I have just taken j to be to the power I theta because it's this contour. I have taken a circular contour. Okay. So yeah, exactly. Then I have taken the real and imaginary part of this equation. Real part still I have to show.
Okay.
Okay. And if you just integrate out over h, you can write down, you can show that your partition function is exactly same as the partition function written in terms of theta's eigenvalues. So therefore partition function, if you do not integrate out h and keep everything, you can write your partition function in this way. Sum of d theta, sum of dhi, write something is nothing but the phase space interpretation. You can give a kind of phase space interpretation of your partition function. Thetas are your coordinates, h's are your corresponding momentum. So you can integrate out, as I say, over dhi, you will get partition function in terms of eigenvalues. That is easy to do, but the other way around is not easy to do. You cannot easily integrate out theta and write partition function completely in terms of h's. That is not easy to do. Okay, so now come back to the real part of that equation. Okay, so this is the real part of the equation. H of theta equals to this. Now one can show that the character remains invariant, okay, if I replace h hi by any even function of theta. Okay, that doesn't change the character. So there is a redundancy, or whatever what is called arbitrary. So in this paper, what we have shown that this f of theta is nothing but pi of theta. So sorry, pi of rho theta. So therefore the final relation we get between h and theta is this part plus a, you can add this even part, and this even part comes out to be pi of rho theta. Okay. So this equation you can get as a solution of this quadratic equation. Okay, it's a quadratic, it has two solutions. These two solutions are nothing but this h plus and h minus. Okay. So in principle you can, so given this equation, and if you now do this identification, u equals to theta by pi, okay, you replace theta by pi of u, and you can invert this equation to write u of h as a function of h. Okay, so this is for the most generic case, generic Cartesian function, at least kind of the class we are considering in vacuum model, but I think it can be generalized to any other Cartesian function also, any other action also. Okay. So now this h plus minus theta basically defines a region in this h theta plane. All the states inside is completely filled, outside it's empty, and so this relation basically defines the boundary of these droplets. And again, this rho theta and u of h are, once I know the boundaries for different phases, I can find rho theta and u of h for those phases. So yeah, so topology of Fermi region is different for different phases of the model, and phase transition corresponds to change of topology of different droplets. So now let me briefly discuss this the droplet pictures for this beta 1, beta 2 model, for which are the eigenvalue distribution I have already discussed. So this is for no gap solution. For no gap solution, h minus is always 0. So therefore the center is always inside the droplet. Okay. This is for one gap solution. Okay. For a fixed theta, so this is h minus surface, this is h plus surface. For a fixed theta, you integrate, you get h plus minus h minus, that is your rho theta. Okay. If you go, so this is your theta 1 angle, minus theta 1 angle, plus theta 1 angle. If your theta is greater than theta 1, you will get eigenvalue to be 0. These are for two gap solutions. So in this case, eigenvalues are distributed between minus theta 1 and theta 1, and then theta 2 and some minus theta 2. Okay. And again, there is nothing between theta 1 and theta 2. So this is for one. This corresponds to. So this corresponds. This distribution corresponds to. This eigenvalue, this phase space distribution corresponds to this eigenvalue distribution, and that other one corresponds to this eigenvalue distribution. Okay, these are two gap solutions. See, in principle, if you have multi-gap solution, then you will get multiple droplets in this h theta plane, and obviously, since as I was telling, eigenvalues are symmetric about theta equals to 0, you see your distributions are symmetric about real axis. Okay, and so you increase your parameter beta 1 and beta 2, at some point what happens that this point touches the origin, and then it becomes a one gap solution that corresponds to your Gauss-Lipton model transition. From no gap to one gap. Okay, and so this is omega of h. If I think of there is some Hamiltonian, and Hamiltonian less than chemical potential gives me the distribution, and Hamiltonian greater than chemical potential, all the states are empty. Then from this relation I can get the Hamiltonian is given by this. And one can also show that this Hamiltonian actually satisfies the Liouville equation, because these are incompressible fluids, these droplets. So this Hamiltonian, if you take this Hamiltonian, they satisfy the Liouville equation. Okay.
You get this Hamiltonian by demanding that the profile, the boundary profile, should satisfy the Hamiltonian equal to mu.
Yeah.
Okay.
Okay. What should I do?
How long would you do it?
Another 10 minutes?
What?
Okay, so I think this is a well known to everybody. This is the partition function of Chern-Simons theory on S3. These are G string, these are known quantities. In this paper, Uda has showed that this partition function can also be written in this way. Okay, so I will start from this point. Okay. So it's a one vacuum model with beta is given by this 1 over n box n. Okay.
What does box n mean?
This is box n. So let me very quickly do the eigenvalue analysis. I define RZ. There are different ways of doing this eigenvalue analysis. One is using this Dyson-Swinger equation. I introduce this resolvent. Yeah, one can show that resolvent is analytic inside the unit circle, okay, in the complex Z plane, as well as outside the unit circle, okay, with this following normalization property, RZ, it should be RZ in plus RZ out 1 over Z, sorry, R out 1 over Z, R in Z plus R out 1 over Z equals 1. And this is not a correct notation. And most importantly, the advantage of this way of solving is that RZ satisfies a quadratic equation in the larger limit. Quadratic equation in the larger limit. So it's very easy to get the solution. Okay. So if I do it, this turns out to be a solution of RZ with some fz. You know, this is some known function fz. Okay. And also, since RZ is analytic inside the unit circle, what we have to do, we have to take GS to be IGS to set all the poles or all the branches of RZ on the boundary of the unit circle. So there is some technique one can we have used to solve to find the eigenvalue density of Chern-Simons theory on S3. Okay.
I'm sorry, maybe this is elementary, but you are doing Chern-Simons on S3.
S3.
So what kind of Wilson lines are we talking about here? What are these eigenvalues?
The Chern-Simons matrix model I can write in this way.
You can write that way. How does it work?
The reference, but if I
mean, where are the non-trivial?
you have some factor. You have this sine theta, theta j factor. What you have, or the potential you have is basically some kind of theta I square kind of potential. If you write down the partition function for Chern-Simons theory.
Oh, I see. So you're saying I see.
So this part, I will do some
Supersymmetric localization. Is this a localization?
This you get by supersymmetric localization. Yes.
Supersymmetric localization. So I just wanted to know the eigenvalues of what quantity, which kind of Wilson line?
No Wilson. I think it's one of these things where you take Chern-Simons theory, then you supersymmetrize it. Supersymmetrization doesn't change the degrees of freedom. This is pure Chern-Simons. Then you do localization. One of the auxiliary scalar fields, it becomes the thing you integrate over, and this is like the eigenvalue from that. So it's not very.
Oh, I see. So one of those
localizations.
Yeah.
Yes.
Amazing.
Okay. So there is a log Z similarity here. Since RZ is analytic inside unit circle, so f square root f log Z must contain a log Z similarity so that it cancels and makes RZ analytic insight. So different forms of FZ corresponds to different types of phases. For example, FZ being a perfect square, okay, gives you a no-gap solution. And once you find FZ, the eigenvalue distribution is given by this. And this is some standard technique. It turns out that for S3 you have only one solution, that is the one-gap solution, and that is given by this. You can find a no-gap solution, but what happens that the corresponding rho theta for no-gap solution becomes negative for some ranges of theta. So that's not a valid solution. And again, if I plot the potential for Chern-Simons theory, it turns out to be a quadratic potential. So it's kind of this kind of potential. So for this kind of potential, you cannot have multi-gap solution. For example, you cannot fill up eigenvalues from here to here, and then you give a gap and then fill from here to here. Then this will not be a minimum free energy configuration. So only possibility is that you have only one gap solution in your model. And this is also, I think, understand from the dual point of view, because this is, I think, related to some topological A model on some result manifold, and this is a topological, there is no phase transition. So you have only one phase in your theory, and this is the phase.
What is T? T is the coupling.
T is the proof coupling, GS times A. Okay. So once I know eigenvalue distribution, then finding out the Fermi surface is trivial. This is the Fermi surface. Okay. So beta n is 1 over Tn. Since you can resum this this quantity sum over n, and this turns out to be the Fermi surfaces. Okay, for the Chern-Simons theory. If I plot it, this is some plot for this phase of Chern-Simons theory. This for t equals to 2. If you increase t, it becomes thinner and thinner, but there is no phase transition. Okay. So this is just an example of what the generic model, what I have discussed. So now I have some outlook and maybe some speculation. I would like your input about these things. So one thing you can notice that constant phase space distribution is very similar to Thomas Fermi model at 0 temperature, while this Wigner distribution is assumed to take constant value inside some droplet and 0 elsewhere. So we are yet to understand the underlying many-body quantum mechanics associated with this phase space distribution. Okay. Also the distributions we get, it's at 0 temperature. Right? So if there is some kind of quantum mechanics, n-body quantum mechanics associated with distribution, the distribution is at 0 temperature. For finite temperature, distribution usually takes this form. Okay, as long as h is less than mu in the 0 temperature, it becomes 1, and h greater than mu at the 0 temperature, it becomes 0. But what is the finite temperature excitation of this underlying theory? These are some speculations. I still have to understand these things. Second, Chern-Simons gas theory on S3 is dual to topological closed string theory on a result on manifold, which is the Bhopal result. Does a phase space description of CS theory will help us to understand a correspondence between topological string theory and some underlying quantum, n-body quantum, many-body system? Is it possible to obtain geometry of dual string theory background from the phase space distribution for a supersymmetric gas theory? For example, we are trying to do it for ABGM. Okay, if I get some kind of phase space picture, droplet picture for ABGM, since it is supersymmetric, the question is, can one construct the dual string theory geometry from the phase space distribution from the droplet picture? What about the program Siraj is doing, Chern-Simons plus matter? What is the phase space description for these things? And I don't think I have time, so there is some interesting relation between eigenvalue distributions of unitary matrix model and non-trivial distribution of non-trivial zeros of Riemann zeta function. So it would be interesting, can I write some kind of quantum mechanics which contains information about both the distribution of non-trivial zeros of zeta function and distribution of prime numbers. So distribution of prime numbers is something related to distribution of Young tableaus in the large entity. So can I write some underlying quantum theory which contains both the information about both the distribution of Riemann zeros, non-trivial zeros, and distribution of prime numbers? So these are some outlook and speculation. I would like to have your opinion about these things.
Bangalore, ICT has questions?
No question.
I do. Okay. Yeah, but
So ALM, is still, even to begin with, it's matrix quantum mechanics. It's not a matrix model.
Yes, yes, yes.
So it's not clear how that works.
True.
Uh,
Yeah, but ABGM, I think, ABGM, phases of ABGM can be written in terms of some droplet pictures. So that actually basically kind of encouraging me. Can this droplet picture be, does it contain any information about the dual geometry?
One question or comment. In these Chern-Simons matrix models, in these Chern-Simons theories, the partition function of the theory on S2 times S1 is given by a matrix model, which is very much like yours, except with one constraint. The constraint is that the eigenvalue density function, rho of theta, can never be larger than 2 pi by 0.
There's a gap.
There's a gap. I was wondering whether if you used your relationship between eigenvalue density functions and representations, you could turn this into a statement of some bound of representations that appear. So there is a natural conjecture for the bound of representations that appear, which is, if you take a Chern-Simons theory, there's a dual Wessoumino-Witten theory. And the natural conjecture would be that the bounded representation should match with the integrable representations of that Wessoumino-Witten theory. I was wondering whether that might work.
One problem is Chern-Simons on S2 cross S1. I mean, the way one start from this expression and write the partition function in terms of SUN plus SUN dagger. This is for S3. They have, at least in that paper, they have done for S3. I have to check whether one can generalize that their algebra, their calculation for S2 process.
In pure Chern-Simons and S2 times S1 as partition function 1. Because you look at it in Hilbert space, there's a unique state on S2. So the partition function. So pure Chern-Simons and S2 times S1 has no physics.
Okay.
So you won't find any literature.
Okay.
It's trivial. However, matter Chern-Simons theories have physics. And in our papers we've rewritten the partition functions of matter Chern-Simons theories after a lot of manipulation into an effective matrix model of the sort you have. The only difference is that the matrix model in the large n limit has the following property, that the eigenvalue density function is bounded from below at 0 but also bounded from above. Now, what I was suggesting was this, forget about how the model comes about. You have a formula which relates eigenvalue densities
And
representations. So just ask, suppose I look at the set of all eigenvalue densities which are bounded from above. That maps to a class of all representations you can consider. I was wondering whether that class of representations is simply the class of integrable representations of the dual recipe. It's a bit of free association, but I think it may be. It might be interesting.
What's an integrable representation?
It's the representations for which you have primary operators in SU. Like in SU2 at level K, the representation ends at K. J ends at K.
I see. So these are called integrable representations. I see.
We mathematicians call them integrable.
I think that model would satisfy me much more, this S2 process one, because at least there is something like a time in that. This is some weird object in which some eigenvalues have appeared because of localization or something, and it's not even clear whether it comes packaged as a unitary matrix. Does it come packaged as a unitary matrix?
partition function you can write in terms
This
of.
Okuda's work.
Yeah.
Does it become a unitary matrix function?
What do you mean? Does it become?
That's
You
great.
take the partition function of the supersymmetric Chern-Simons theory on S3. Okay, as Shiraz was explaining, you use the machinery of localization, and then there is a sort of moduli space of this saddle point in localization, and that is given by the eigenvalues.
Yeah.
But they appear as eigenvalues of a unitary matrix.
It actually, I mean, if you do this localization, it actually comes as some sine hyperbolic, theta I minus theta j by 2 square, some theta I square. These are some it actually comes as sine hyperbolic.
Fine,
We have to do a theta I
yeah,
to I theta.
But these theta is a what?
I think they were eigenvalues of some auxiliary scalar field.
Yeah.
Auxiliary scalar.
Some auxiliary scalar field. There wasn't even some angle thing. That's why there was some sign.
In fact, if you look at Okuda's paper, Okuda actually didn't do it in terms of this localization. He actually started from that original expression of Witten's.
Oh.
Okay, and then he used some identities. He actually started from this expression, and then he used some group theory mathematical identities, and also used what is called this theta zero function, Jacobi's theta function, identities of Jacobi's theta function, and wrote Jacobian it in this form. He didn't actually use the localization technique to write the partition function in this way, and then he actually started from that expression. He did some used some mathematical identities, and then finally got this expression using some theta function identity.
I mean, you seem to have some hidden quantum mechanics somewhere.
Seems
This,
that is not that
yeah.
is something seems to me, yeah.
Sorry. Aaron,